Here is section 10.1, properties of gases. So we're going to look at a little intro into the gases here. This is a state of matter that we're discussing. You are probably familiar with the idea that we have solids, and solids have particles, atoms, or molecules that are tightly packed together. The atoms are right on top of each other. Solids are rigid, so the atoms or molecules are not free to move around with respect to each other. Then we have liquids. And liquids, the atoms or molecules are pretty closely packed, generally a little bit less so than solids, but not by much. One exception is water. In water, the molecules are more closely packed than liquids. But for most materials, the liquids are a little bit less closely packed. Liquid molecules or liquid atoms are able to move. They're able to rotate and translate and move with respect to each other. They flow, right? You can pour a liquid, but you don't pour a solid. And then you have gases, and gases are even more free to move around. The molecules are generally very widely spaced, so far apart that they generally don't interact with each other. They're moving in straight lines. Occasionally they collide with each other and go other directions, but they're very large distances between them. Okay, so we're going to focus on gases here. So gases will essentially take the shape and volume of the container. And that's different than a liquid or solid, right? So for example, if you have a container and you put a gas in it, the gas molecules will spread out and take on the shape and the entire volume, the entire space of the container. Now that gives gases physical properties that are different than solids and liquids. In fact, in many ways, gases are much more predictable in terms of their behavior, meaning that if you heat a gas, it's predictable how it will behave, how it will respond. That's not quite so true with solids or liquids. Okay, so let's take a look at some of the common gases. On the periodic table, there are several elements that are gases at room temperature. And atmospheric pressure. Okay. So we should point out that under the right conditions, pretty much any element can be a solid or a liquid or a gas. But at room temperature and atmospheric pressure, these are the elements that are in the gaseous phase. So you're familiar with some of them. There's hydrogen, right? Hydrogen. There's helium. There's nitrogen, oxygen, fluorine, and neon in the second row of the periodic table. In the third row, there's chlorine and argon. In the fourth row, krypton. In the sixth row, xenon, and then in the seventh row, radon. So those are the elements. There's not very many of them if you think about it. 11 elements out of the entire periodic table are gases at room temperature. Okay? Let's remind ourselves that some of these are gases, but they're also diatomics, right? So these are diatomic elements. Of course, hydrogen is one of them. Nitrogen, oxygen, fluorine, and then chlorine. Those are the diatomic elements that are gases at room temperature. Okay? The other gases, helium, neon, argon, krypton, xenon, and radon, those are the noble gases, right? Those are noble gases, and they are elemental, and they're also monatomic gases. So these are what are called monatomic. meaning one atom. So a helium atom is just one. But if we were to look at oxygen, we would find that its more common form is O2, two oxygen atoms bound together. Okay? Now there are also gases in terms of compounds. Many compounds exist as gases. Far too many for us to list all of them, but let's go through a few of them. These gases are listed in table 10.1 of your textbook. So these are gaseous compounds. Again, at room temperature and atmospheric pressure. Okay, so one of them is HCl, hydrogen chloride. Now we're familiar with HCl as being hydrochloric acid, right? But actually as a pure substance, it's a gas. It's HCl. It's when you dissolve it into water that we think of it as a strong acid, HCl, hydrochloric acid. Okay, so there's one. Here's another one, ammonia. Ammonia, the common name ammonia, is also a gas. NH3 is a gas at room temperature and standard atmospheric pressure. There's carbon dioxide, right? We've all heard of carbon dioxide. It is the important compound produced through combustion. There's nitrous oxide. Now we've heard of nitrous oxide. Sometimes it's called laughing gas, right? Dentists use it as a sedative, essentially, to relax people. There's methane, which is is the primary component of natural gas. Okay, so this is what you find in natural gas. It is not the only gas in natural gas, but it's the primary one. There's also HCN, which is called hydrogen cyanide. Hydrogen cyanide is famous for being used in the old, what are called gas chambers, as a way to execute people, as a very poisonous, very toxic gas. Okay, so again, this is not a comprehensive list, but it's a list of some of the gases that are compounds. So one thing that's important about gases, one property of gases that we should be aware of, is that gases are compressible. And that is an interesting aspect of them, an interesting property of them that gases do not share. They don't have this property in common with liquids or solids. Liquids or solids, if you push down on them, they might move or they might not move, but they will not compress. They will not get smaller. Gases, on the other hand, if you push down on them, you can compress them into smaller volumes. This is an aspect of thermochemistry when we talk about doing mechanical work by compressing a gas. So if we have a gas inside of a cylinder and we push down on the piston, the piston might move all the way down here, and now the gas is occupying a very small volume, right? So the gas is compressible. You can compress it into a smaller volume. Okay, that's an important aspect of them as well. They also mix easily. So for example, if we have a tank, oops, with a little hose here, and then we take another tank here. This has a gas in it. And we put those hoses into a mixing chamber. So here's gas 1 and gas 2. and we allow the gases to flow through these tubes, the gases, those two gases, will mix perfectly, essentially, almost perfectly. Okay, so they will mix to form what's called a homogeneous solution. Okay, a mixture in which the molecules are perfectly distributed amongst each other. Okay, that's a property of gases that are generally different than liquids or solids. Okay, we can also talk about density. The density of gases they're much smaller than liquids or solids. They have much lower densities than solids or liquids. Okay. So for example, we're all familiar with liquid water, right? Liquid water has a density of about a gram per centimeter cubed, a gram per milliliter, if you want to use those units. Milliliters is the volume unit. Okay, so that means that in a cubic centimeter, so imagine a centimeter as being the width of one of your fingers, essentially. So if you look at one of your fingers, your index finger, and you just measure from one side to the other, okay? That's about a centimeter. Okay. So what that tells us is that if you take a volume, a cube, that's 1 centimeter by 1 centimeter by 1 centimeter. If you put liquid water in there, that would weigh about a gram. Okay, so that's what the meaning of density is, 1 gram per centimeter cube. It means that the mass of that water would be a gram. Now, if you were to do the same thing with a typical gas, like oxygen gas, at room temperature, what you would find is that the density is much smaller. It's about 0.001 gram per centimeter cubed. It's about 1,000th the density, 1/1000th the density of the liquid. Okay, very low density. So gases are generally much less dense than solids or liquids. The reason for that is that gases have large spaces in between them, huge spaces in between. And so if you have huge spaces in between, then you're not going to be very dense. Whereas solids and liquids, the atoms are very close to each other, so they're going to be more dense. Okay? So that's a physical property, or a few physical properties of gases that distinguish them from solids or liquids. Now what we're going to do is we're going to look a little bit at the depth or in detail at the issue of pressure. Okay? At gas pressure, essentially, what we're going to look at here. So let's take a look at gas pressure. Now, if we consider the Earth, we're going to take the surface of the Earth. And we note that we have an atmosphere above it, right? There's an atmosphere above the surface of the Earth. And if we take a look at a column of air, so air is most dense near the surface of the Earth. It becomes less and less dense as you move higher and higher up. But remember, the atmosphere is miles thick. In a sense, it's 100 miles thick, or at least near that. So if you were to add up the mass of all those air molecules going from sea level all the way up to 100 miles, it would have a certain weight to it. So how much does it weigh? How much does the atmosphere weigh? Well, one way of thinking about it is to ask the following question. What is the weight of the atmosphere divided by a given area, divided by a specific area? Okay, so that could be in centimeters squared or inches squared or miles squared if you wanted to do it that way. Historically, using English units, Weight is measured in pounds. And area could be measured in inches squared. I'll put inches in parentheses there. So one way of naming this would be to say it's pounds per square inch, right? And we'll abbreviate that as PSI, okay? So one way of measuring how much the atmosphere weighs divided by an area, arbitrarily pounds for weight and inches squared for area, we would call the units of that pounds per square inch. And what you find is that if you take at sea level, if you take an area of an inch squared, okay, let me draw this as an inch squared. So 1 inch height, 1 inch length. That's an area of an inch squared. The weight is 14.7 pounds. And so we would say that the weight divided by the area at sea level of the atmosphere is 14.7 pounds per inch squared, or pounds per square inch. So what that means is every square inch at sea level that is exposed to the atmosphere has a weight of about 14.7 pounds on it. Okay? So imagine, let's say you had some piece of paper, and let's say that this was 100 inches squared, 10 inches by 10 inches, for example, which is not that far off from the size of a piece of paper, right? The amount of weight that this paper is exposed to as it sits on the table at sea level would be 14.7 pounds per square inch times 100 inches squared. Well, that's 1470 pounds, right? That's a huge weight, right? So it's strange, or it's surprising in a sense. We don't normally think of it as being that heavy, but the atmosphere actually does put quite a bit of force onto us. So let's remind ourselves that weight is an example of a force. And so since we're dividing weight by area, this would be a force divided by an area, and force divided by area is called a pressure. So we would call this 14.7 psi the atmospheric pressure of the Earth. And of course it depends on the altitude that you're at. As you move to higher altitudes, the pressure decreases. You can sometimes experience that on an airplane or even in a car. You hear a popping in your ear because the pressure of the atmosphere is changing as you move from one altitude to another. Okay? So pressure. So what we should do at this point is talk a little bit about units and conversions, at least a little bit about it, and also how we measure pressure. So one aspect of chemistry is that we measure things, right? So we want to talk a little bit about that. But I want to point out, first of all, that if you are standing at sea level, the atmosphere is exerting a force on every square inch of your body at the same time. And you're probably not aware of it, but it's a very large force, a large pressure that we're exposed to. Move to outer space, move outside of the Earth's atmosphere, and you would be very well aware very quickly that there's something going on there. So I want to talk a little bit about this kind of famous little picture that's in your textbook, figure 10.3. And what they do there is they take a little gas tank, just a little metal tank with a lid. and they hook it up to what's called a vacuum pump. And so what the vacuum pump does is it's a mechanical device that essentially pulls the air out of this tank and then throws it out into the atmosphere. And once you've done that, once you've pumped all of the air out of this tank, you now have a vacuum. Okay? So what is a vacuum? A vacuum is nothing. A vacuum is where you've taken everything out. So once you get all of the air out, you now have a vacuum. Okay? So what's significant about this is they show you what happens when you do that to a metal tank. So the metal tank we're talking about is like an aluminum can or something like that. So once you have a vacuum, there is a pressure of gas from the atmosphere, atmospheric pressure, right? Pushing in on the can in all directions. But there is no longer any gas on the inside to push back out. Before you have a vacuum, what happens is the gases on the inside are pushing out and the gases on the outside are pushing in, so the container is pretty stable. But once you pull a vacuum, once you get all of the gases out of that container, now there's no force outward, there's only a force inward. And what happens is it crumples. It's really quite a remarkable thing. It just crumples into a little can. And the reason for that is because, again, there's an excess pressure on the outside relative to the inside. And so even a metal container isn't strong enough to withstand that enormous force exerted by the atmosphere. Okay? Now, we ourselves would be compressed as well by the atmosphere, except for the fact that we're made out of primarily liquid, water, solids and liquids, bones and all that. So remember, liquids and solids are not compressible, but gases are. Okay. Now, let's talk a little bit about the units of pressure, and this is in table 10.2. So the most common unit of pressure is what's called standard atmosphere. Standard atmosphere is essentially the pressure of the atmosphere at sea level. And so we're going to say that at sea level, the pressure of the atmosphere is 1 atmosphere or 1 standard ATM. Okay, a standard ATM. But there are other units as well. So there's something called the millimeter, MM for short, for abbreviation, millimeters of mercury. What's the symbol for mercury in the periodic table? Hg. Mercury is Hg. So this is called millimeters of mercury. We'll talk a little bit in a moment about why this is a particular unit that's used. It's used in what are called barometers. Okay? And 1 millimeter of mercury, let me put it this way, 760 millimeters of mercury is called an atmosphere. Okay? So 760 millimeters of mercury is equal to a standard atmosphere. So that's a conversion factor. Okay? Now there's also something called the torr. And the torr is essentially the same as a millimeter of mercury. So this is also used in barometers. And so 760 torr, is equal to an atmosphere. In other words, 1 torr, is equal to 1 millimeter of mercury. Okay? Just a different name for a millimeter of mercury. It's named after Torricelli, who is a historic figure in science. There is also what's called the bar. And this is used in, it's what we would call a MKS unit. Okay? And we'll talk a little bit more about that in a moment. I'm not even going to give you the conversion factor here. The bar is approximately equal to an atmosphere, but it's off a little bit. Okay? So let me talk a little bit about MKS units. Okay? Remember, MKS is meter for length. So any measurement that involves length under the MKS system is meters, kilograms for mass, and seconds for time. So this is called the MKS system. And if you remember back in chapter 5, I talked about how in chemistry we sometimes use the CGS system. And the CGS system is centimeters, grams, and seconds. So two of the units are different than the MKS system. So one of the issues that arises here is that historically people use different units to measure the same thing. So pressure is no different from that. Pressure has many different units that are used. So what I want to do is I want to give you the standard MKS definition of pressure. So pressure we're going to call force over area. So let's use symbols, F over A. Okay, force divided by area. So what we're going to do is we're going to say that we have something called the Pascal. That's a unit of pressure. And the abbreviation for that is a PA, capital P, lowercase a. So the Pascal is the case where you have 1 Newton. That's a unit of force divided by a meter squared. That's called a Pascal. Now let's go ahead and abbreviate the Newton. It's 1N divided by m squared is a Pascal. Okay? So under the MKS system, the units of pressure are in pascals, and a Pascal is a force of a Newton, a weight is a force of a Newton divided by a meter squared. Okay? Now the problem with that is that the atmosphere is much larger in pressure than a Pascal. The atmosphere is actually 101,325 pascals. Pretty large, right? That's a pretty large pressure in terms of pascals. So generally what we do then is we use a prefix for the pascals. We use kilo, 1,000. So remember, 1,000 is kilo. So in kilopascals, this would be 101.325 pascals. Okay, so not comma, but point, meaning 101, approximately 101 pascals is an atmosphere. I'm sorry, kilopascals. I forgot to put the kilo in there. Okay, kilopascals. So 101,325 pascals or 101.325 kilopascals. So that's a little bit inconvenient. Ooh, I'm sorry, I made a mistake. It's 100,000. I don't know why I made the mistake. 100,325. There we go. 100,325. So what happens is that number, 100,325 or 100.325 kPa, is tantalizingly close to 100. It's really, really close. But it's not exactly there. So here's what we do. We define something called a bar. And a bar is almost an atmosphere. Okay? A bar is 100 kilopascals. So it's not exactly 100,325, but it's pretty darn close. Okay? So for that reason, what we do is we go ahead and define this unit called the bar, and it's 100 kPa, and we can use that instead of the standard atmosphere. And I'm sorry, I'm going to come back here. I was right the first time. This is 101,325. Okay, so the bar is 100 kPa, and that makes the pressure just easier to deal with. So some chemists and some physicists and some geologists will use bars as a measure of pressure instead of atmospheres. So common unit to be used. So now there's several units that we have in here, right? We've got atmospheres, we've got bars, we've got kilopascals, we've got pascals, we've got millimeters of mercury, we have torr. A lot of units, right? So that's just one of the things that we have to deal with, is that there's a lot of units of pressure that are used out there. And it just sort of depends on who you are and what kind of work you do in the sciences as to what units you're going to use. Okay? Now, let's talk a little bit about measuring pressure. How do we measure pressure? One way is through what's called a simple barometer. It's probably the easiest way to measure pressure. So what you do is you take a container, like a cup, and you fill it with a liquid. Okay, so there's a liquid in this container. Preferably, this liquid has a high density. Preferably. It doesn't have to, but it's easier if it does. Then what you do is you take a tube, which is open on one end and closed on the other, and you put it in upside down, like a test tube. So it's an upside down test tube. And what happens is the atmospheric pressure pushes down on the surface of the liquid. And it pushes the liquid up this tube to a certain height. And the height of that liquid in the tube is directly proportional to this atmospheric or external pressure, the pressure of the air outside of the tube. So if the pressure outside goes down, the height of the liquid goes down. If the pressure increases, the height of the liquid goes up. So what we do is we measure the height of the liquid in the tube from the surface of the liquid to the top of the liquid in the tube. And we call that height h. And that height is proportional. That's the proportionality sign to the external pressure of the atmospheric pressure. Okay? Proportional to, not equal, but proportional. So let's think about it. Let's go back to our units. Remember we had this thing, millimeters of mercury? 760 millimeters of mercury is an atmosphere. Now we have an explanation for the meaning of that. What that means is that under normal conditions at sea level, if you were to put mercury in this pool and in this tube, the height of the mercury would be 760 millimeters, which, by the way, is 76 centimeters, which is 0.76 meters. So that's a little bit more than 3/4 of a yard. Okay? So more than 2 feet. So the reason that mercury is used is because it's very high density. And here's what happens. The pressure of the atmosphere is equal to the pressure of the weight of that mercury divided by the area. Okay, so what you can do is you can say that the pressure is equal to the height times the density of the liquid, D, for density of the liquid, so in this case mercury, times the gravitational acceleration of the Earth. Okay? So the density of mercury, I'll write Hg for mercury, is around 13.6 grams per centimeter cubed, or around 13,600 kilograms per meter cubed, if, meter squared. Oh, meter cubed, sorry. This is density, so that's cubed. So that's the density in the CGS system, grams per centimeter cubed, and the MKS system, kilograms per meter cubed. And then G is the gravitational constant of the Earth, and it's around 9.81 meters per second squared in the MKS system. Okay? So let's do the sample problems. Make sure you try the sample problems for this so that you get a chance to actually look through these problems, so you get a chance to do the calculations with this. All right. There is another way to measure pressure, but this is not measuring the pressure of the atmosphere, it's measuring the pressure of a gas in a container. So let me show you that. This is called a manometer. So this is how you measure the pressure of a gas. Okay, not the atmosphere, but a gas. So the manometer, there's a couple different types, but let me show you one of them. What you do is you have a container. It looks something like this. So your gas is in here, and then there's an opening that comes down like this. And then this can be opened or closed here. Little valve there for opening or closing. Okay? So what you do is you fill it with mercury. Mercury is dense, so it falls down to the bottom. Okay? And then in here is a vacuum. So now the gas is in here. So what happens is the gas flows in here, and it exerts a pressure on the mercury. I should put a little bit more mercury in there. There's not enough mercury in there. So as the gas pressure increases, meaning if you have more gas in there, its pressure will be higher, it'll push the mercury up this way. And let me erase it down here. And it'll push it away from here. Okay? So now what happens is you've got a height differential here, from here to here. So that height is proportional to the pressure of the gas. The more gas that's in here, the more it'll push that mercury up. And it doesn't have to be mercury, it could be alcohol, or it could be water. You could use something else if you want to. Okay? So there you go. That's a way to measure it right there. Now, that is essentially a nice little introduction into the properties of gases, but really the issue here is the pressure of gases. We're going to be using pressure in our calculations. So make sure you try sample problem 10.1. Try the checkpoints as well so that you can do some conversions of pressure units.